Good morning, everyone. Today I will present my homework for number 2. The main tests here are to create a MATLAB model for the spring damper system. First, let's clearly what we need to do in this part. First, build a MATLAB model for our spring damper system. To draw the step response curve. 3. Conclude the setting time. The tools we will use are from MATLAB Control System Toolbox. We need three key functions. TF to create to the transfer function model. Step to plot the step response curve. Step info to get important value like setting time from the response. Why is this useful for engineering? This method isn't just for our simple system. It can be used for more complex systems too. It's a common way to analyze how medical systems move and respond. Also, we will use MATLAB for this work. Now let's look at the first part of the MATLAB code, defining parameter and building the transfer function. First, we set the value of the system parameters. M is 1 million. The mass of the block in kilograms. B is 50. The damping conflict of the jumper F is 500. The input force will apply. Next, we build the velocity transfer function. This is the same transfer function we derived earlier. Just to connect this to our earlier theorem, this transfer function matches the standard first order from here. Actually, what we concluded before. The next part of the code is for plotting the step response. Let's break it down. Finkel. This opens a new window for the plot. The step function drawing the response we multiply by SYSV because we want to see how the velocity responds to the 500 force. Title. Add the title to the plot. X label labels the x-axis time, second. Y label labels the y-axis grid on, adds grid line to the plot, making it easier to read. Now let's analyze the plot using the curve start at 0. The mass is at rest and raise up to a standard speed. This standard speed is 10 meters every second. We can check this with the final value sensor from our theory, which confirms this number. The curve has 3 passes. rapid responses, the speed increases quickly at first. Convergence pass. The speed slows down as it gets closer to the standard value. Steady state pass. The speed stops changing and stay at 10 meters every second. A quick thought for exertension. If we increase dumping, the curve becomes steeper. This means the system reaches standard speed faster. If we increase, the curve becomes flatter. This is because more mass means more intermitting. So the system sped up more slowly. Now let's conclude the setting time using MATLAB. Here's the code. First, what is setting time? It's the time it takes for the system response to reach the steady value and stay with a small error bar. Usually 5% or 2% of the standard value. Now let's check if the simulation matches our theory. For first order system, the heuristic setting time is about 4 or 3. The MATLAB result is 78.24 seconds. This is very close to the 80 seconds. The small difference is normal for simulations, and it proves our mode is correct. Let's summarize the key characters of the system we found. First, standard state value, final speed. This is determined by F or B. More force or less damping will make the standard speed higher. Setting time. This is determined by the time constant. A large means a longer settle time, so the system takes longer to reach standard speed. Which engineering insights can we got from this? If we want the system to respond faster, we have two options. This is useful in real engineering. For example, when operating cars suspension, engineers might choose later parts or better dampers to make the sensors respond faster and keep the car stable. The memory. Let's work up this part of the homework. First, we review key knowledge. MATLAB tools using TF to build model, step to plot response, and step in of to get settle time. What a step response cover looks like and what it tells us. Checking if simulation results may match theoretic calculations like setting time. The logic we followed is an engineering loop. 1. Start with the sensory model. 2. Build a MATLAB solution model. 3. Analyze the simulation result. 4. Turn those results into practical engineering insights. The lab completes the process of model to simulation application, showing how theory can be used to solve real engineering problem. This is all my answer. Thanks for your listening. Goodbye.